I'll do some more problems based on current density. The problem is the current density in a certain region of space is given by vector j equals minus 10 to the power 6 e to the power minus x into minus sin y ax cap plus cos y ay cap amperes per meter square. Find the current crossing the surface xyz varying between 0 and 1. That means it's a cube by two different methods. So the solution will start. So x, y, z varies from 0 to 1 means, as I said, we have a cube of side equal to 1 meter. Correct. We have taken one of the corner of the cube as the origin. Because x, y, z varies from 0 to 1. Correct. In this front face is at x equal to 1. Back face is at x equal to 0. The right face is at y equal to 1. Left face is at y equal to 0. Top face is at z equal to 1. Bottom face is at z equal to 0. Here bottom face doesn't come into play because there is no az cap. From the given expression, what is jx? What is jx? Jx is coefficient of ax cap. So it is 10 to the power 6 e to the power minus x into sin y. Minus into minus, it is plus. What is jy? Jy is equal to minus 10 to the power 6 e to the power minus x into cos y. This is the expression for, from the expression for vector j, we have found what is jx and jy. Now we'll apply the formula I is equal to closed surface integral vector j dot ds. This closed surface integral is split into 6 open surface integrals. Vector j dot ds. This is for front face. Front face is at what value of x? X is equal to 1. Plus integral vector g dot ds for back face. Back face is at x equal to 0. Plus integral j dot ds for right face. Right face is at y is equal to 1. Plus integral vector j dot ds for left face. This is at y equal to 0. I do not consider top and bottom faces because jz is 0. No need to consider the top and bottom faces. They will not contribute because jz is 0. This implies I is equal to, correct, front face, double integral, vector j is what? Jx into ax cap dot. What is dsx? dsx into ax cap. This is at x is equal to 1. dsx means what? dsx means dy into dz. I'm going to write here dsx means dy into dz. dsy means dx into dz. So dsx means what? Dy into dz. Y varies from 0 to 1. Z varies from 0 to 1. Front face. This is for front face which is at x equal to 1. Plus double integral. For back, see, back face, it is vector j is entering. Entering means we have to take a minus sign. What leaves is taken as plus, what enters is taken as minus. So this is what? Jx into ax cap dot minus dsx into ax cap. Why this minus sign? Because at the back face vector jx is entering. What entering? What enters is given a minus sign. So here y varies from 0 to 1, z varies from 0 to 1, and back face is at x equal to 0. Plus double integral vector j dot ds. So this will become, so here vector j is jy into ay cap dot. Actually you might be wondering why I have not taken jy while evaluating this expression. Even if you write, it's of no use because ay cap dot x cap will become 0. Therefore no need to write jy component when dsx has got the unit vector ax cap. So this is jy into ay cap dot dsy into ay cap. The right face is at y equal to 1. What is dsy? Dsy is dx into dz. Therefore, x varies from 0 to 1, z varies from 0 to 1, plus double integral, again x varies from 0 to 1, z varies from 0 to 1, jy ay cap dot minus dsy into ay cap. Minus sign because to the left face jy is entering. What enters is treated as minus. So j in the expression for jx, if you put x equal to 1, you get 10 to the power x, 10 to the power 6 into e to the power minus y into sin y. So this implies I is equal to double integral from 0 to 1. If you put x equal to 1 here, you get what? 10 to the power 6 into e to the power minus 1 sin y. Then what is dsx? dy dz. Then this minus sign you take out, double integral, y varying from 0 to 1, z varying from 0 to 1. What is jx? If in this expression for jx, if you put x equal to 0, e to the power minus 0 is 1. Therefore, you get 10 to the power 6 into sin y. dy dz plus. Next, I will come to this double integral, x varying from 0 to 1, y varying from 0 to 1. In the expression for jy, you put y equal to 1. So what happens if you put y equal to 1? You get minus 10 to the power 6 e to the power minus 6 into cos 1. Here 1 is in radians. Please note that 1 is not degree. This is the expression for jy when you put y equal to 1 here. And what is dsy? Dsy is what? dx dz. This is dx dz. Plus this minus sign, if you take out minus, double integral from 0 to 1, x varying from 0 to 1, z varying from 0 to 1. This is evaluated at y equal to 0. So in the expression for jy, if you put y equal to 0, cos 0 is 1. So you get minus 10 to the power 6 into e to the power minus 6. Cos 0 is 1. dx dz. So you have to evaluate these 4 integrals. If you evaluate these 4 integrals, you will get answer as 0. So that evaluation I leave it to you. It's not difficult. Please note that when you evaluate this, let me go further and leave it. This implies I is equal to 10 to the power 6 into e to the power minus 1. Sin y, if you integrate, you get minus cos y, limits from 0 to 1. dz, if you integrate, you get z between 0 and 1. Correct? Sin y, if you integrate, you get minus, this is minus 10 to the power 6. Sin y, if you integrate, you get minus cos y between 0 and 1. dz, if you integrate, you get z between 0 and 1. Come here. So this is minus 10 to the power 6, minus 10 to the power 6 into cos 1 you take out. E to the power minus x, if you integrate, you get minus e to the power minus x, x varying from 0 to 1. Then dz, if you integrate, you get z, limits from 0 to 1. Minus into minus, it is plus. 10 to the power 6 you take out. E to the power minus x, if you integrate, you get minus e to the power minus x, limits between 0 and 1. dz, if you integrate, you get z between 0 and 1. If you put the values for, if you put the limits, you will get the answer as 0. This you please check. The answer is 0. So the evaluation of the integrals is being very clearly explained to you. So please evaluate, you will get the answer equal to 0. Next, what I am going to do is, I am going to verify this by another method, 0 amperes. Second method. Second method. I is equal to what? Closed surface integral vector j dot ds. By applying divergence theorem, we get this closed surface integral is converted into a volume integral. Instead of vector j, I write del dot j dv. This is nothing but volume integral. What is divergence of j? Dou jx by dou x plus dou jy by dou y plus dou jz by dou z. What is dv? dv is what? dx, dy, dz. So this becomes volume integral. If you differentiate this with respect to x, what you get? Dou jx by dou x is what? 10 to the power 6 into e to the power minus x into sin y. If you differentiate this with respect to y, what you get? Minus 10 to the power 6 e to the power minus x. Cos y, if you differentiate with respect to y, you get minus sin y. Then it is dx dy dz. Volume integral is a triple integral. Okay, volume integral is a triple integral. X varies from 0 to 1, y varies from 0 to 1, z varies from 0 to 1. These two terms are equal and opposite, therefore 0 dx, dy, dz. So the answer is 0. In the first method you got 0. When you did the same problem by another method which involves the application of divergence theorem to this closed surface integral, again you get the answer of first method. Therefore we have in fact verified divergence theorem. First we have evaluated the closed surface integral, then we have evaluated volume integral, and hence showing that both methods give the same result. Thank you. Next problem. In a certain region of free space, the electric potential is found to be V is equal to 150 into x to the power 4 by 3 volts for x greater than 0. Find part A, vector E, vector D and rho V as functions of x. Find Jx at x equal to 0 and x equal to 1 meter if velocity ux equals 3 into 10 to the power 6 x to the power 2 by 3 meters per second. So we'll crack this problem. We'll do first part here. V is given, so what is vector E? Vector E is equal to minus grad V. Correct? And in Cartesian coordinate systems, expand gradient, you get dou V by dou x into Ax cap plus dou V by dou y into Ay cap plus dou V by dou z into Az cap. So dou V by dou x is what? X to the power n. If you differentiate, you get nx to the power n minus 1. So this is 150 into 4 by 3 into x to the power 4 by 3 minus 1 means 1 by 3 Ax cap. These two terms will be 0. Because V is a function of x only, dou V by dou y will be 0 and dou V by dou z will be 0. So this is 600, 150 into 4 is 600. 600 by 3 is 200. So this is minus 200 x to the power 1 by 3 into Ax cap. So many volts per meter. This is the expression for This is the expression for vector E. Next I will find vector D. Vector D, we know that vector D is equal to epsilon into vector E. It is given the problem free space. Therefore, epsilon is epsilon naught. So it is minus 200 epsilon naught into x to the power 1 by 3 into ax cap, so many coulombs per meter square. This is the expression for vector D. Next, what is rho v? Right, Gauss law in point form is, Gauss law in point form is divergence of D is equal to rho v. This implies rho v is equal to dou dx by dou x plus dou dy by dou y plus dou dz by dou z is equal to dou by dou x operating on, what is the coefficient of ax cap is what? Dx. So it is minus 200 epsilon naught x to the power 1 by 3. dy is 0, dz is 0, therefore the other two contributions are 0. Therefore the other two contributions are 0. This implies rho v is equal to, differentiate this with respect to x. So it is minus 200 epsilon naught 1 by 3 x to the power minus 2 by 3. Nx to the power n minus 1. So 1 by 3 minus 1 is what? Minus 2 by 3. So this is 1 by 3 into x to the power minus 2 by 3. This is the expression for rho v. It is in coulombs per meter cube. Next part is, what is Jx? We know that vector J is equal to rho v into vector u. Expression for convection current density. This implies, what is vector J? Jx into Ax cap. What is vector u? Ux into Ax cap. This implies Jx is equal to rho v into Ux. What is rho v? Rho v we have calculated. What is rho v? Minus 200 into epsilon naught into 1 by 3 x to the power minus 2 by 3. This is the expression for rho v taken from here. What is the expression for Ux? Expression for Ux is 3 into 10 to the power 6 into x to the power 2 by 3. So many amperes per meter square. This expression has to be now evaluated at two different values of x. Hence Jx at x is equal to 0. If you put here x equal to 0 in this expression, the answer is 0. And Jx at x is equal to 1 meter. In this expression, you put x equal to in this expression you put x is equal to 1. 1 to the power anything is 1. So you get minus 200 into epsilon naught into 1 by 3 into 1. 3 into 10 to the power 6 into 1. So this is the expression for Jx at x is equal to 1 meters. So when you put x equal to 1, 1 to the power minus 2 by 3 is 1. 1 to the power 2 by 3 is also 1. Or when you multiply these two, x gets cancelled out. Okay, sorry. When you multiply x to the power minus 2 by 3 and x to the power 2 by 3, you get x to the power 0. That means Jx will become independent of x. Therefore, this is not 0. Jx at x equal to 0, also same answer. Minus 200 into epsilon naught into 1 by 3 into 3 into 10 to the power 6. Effect of x gets cancelled out because x to the power minus 2 by 3 into x to the power 2 by 3 is 1. Therefore, Jx at x equal to 0 and Jx at x equal to 1 will give identical answers. Thank you. Next problem. Find the total current crossing the surface z equal to 3 and rho less than 6 in the az cap direction if vector j is equal to 100 by rho square a rho cap plus 10 by rho square plus 1 Az cap amperes per meter square. Also find dou rho over dou t. This problem is given in a cylindrical coordinate system. We'll first solve part A. From the given expression, what is J rho? Coefficient of A rho cap is J rho, which is 100 divided by rho square. What is Jz? Jz is 10 divided by rho square plus 1. What is J phi? J phi is 0. J phi is 0 because there is no A phi cap unit vector in the expression for vector J. Now first we will find current in which direction? Az cap direction. So current I is equal to surface integral vector J dot ds. He has told in which direction? He has told the direction should be Az cap. Therefore vector ds should be dz into Az cap. Correct? And what is vector J? Vector J is what? Vector J is J rho A rho cap plus Jz Az cap. This is vector J. If you take dot product of this vector with vector ds, A rho cap dot Az cap is 0. Az cap dot Az cap is 1. This implies I is equal to surface integral double integral. He will be left with Jz into dsz. Please note that why I have taken vector ds as dsz into Az cap, because he has asked what is the total current crossing the surface in the Az cap direction. If you had asked A rho cap direction, then instead of Az cap I should have written here A rho cap. Instead of dsz I should have written ds rho. Please note that. So dot product of A rho cap and Az cap is 0. Dot product of Az cap and Az cap is 1. In a cylindrical coordinate system, dl1 is d rho, dl2 is rho into d phi, dl3 is dz. Therefore, dsz is dl1 into dl2, which is d rho into d phi. So, rho varies from where to where? 0 to 6. 0 to 6. This is the variation of rho. Phi varies from 0 to 2 pi in a cylindrical coordinate system. And if you look at the expression for Jz, it is 10 divided by rho square plus 1. So this becomes now, this implies I is equal to, actually this expression must be evaluated at z equal to 3. But since Jz is independent of z, correct, the z equal to 3 has got no significance. For example, in the problem Jz, if it were given 10 divided by rho square plus 1 into z assume, then when you put z equal to 3, the value of Jz will be 10 by rho square plus 1 into 3. Here z equal to 3 has got no significance. So this is Jz double integral, correct? Rho varies from 0 to 6, phi varies from 0 to 2 pi. What is Jz? 10 divided by rho square plus 1. And what is dsz? Rho d phi. This is the expression for dsz. Rho d phi, which I have copied from here. So this is now, you write this as 5 into integral 0 to 6, correct? 2 rho divided by rho square plus 1. This 10 I have written as 5 into 2. This is now 2 rho divided by rho square plus 1 into integration from 0 to 2 pi d phi. See, 2 rho is the differential of rho square plus 1. So if numerator is the differential of the denominator, you get log function. So this is nothing but this implies I is equal to 5 into natural logarithm of rho square plus 1. Rho taking values, lower limit is 0, upper limit is 6. d phi, if you integrate you get phi, lower limit is 0, upper limit is 2 pi. Put the values and keep the answer. This is how we find the current I. Next is we have to find dou rho v by dou t. To find dou rho v by dou t, we make use of equation of continuity. Recall divergence of j is equal to minus dou rho v by dou t, nothing but equation of continuity. Using equation of continuity, we have to find dou rho v by dou t. This implies dou rho v by dou t is equal to minus divergence of j. Divergence of j has to be now written in a cylindrical coordinate system. What it is? 1 by rho, dou by dou rho operating on rho into j rho, plus 1 by rho, dou by dou phi operating on j phi, plus dou jz by dou z. This is the expression for divergence in a cylindrical coordinate system. Equals minus sign I keep out 1 by rho, dou by dou rho operating on rho into what is j rho? J rho is 100 by rho square, 100 by rho square, plus 1 by rho, dou by dou phi operating on j phi. What is j phi? J phi is 0, plus dou by dou z operating on jz. What it is? 10 divided by rho square plus 1. So now this is minus 1 by rho into, this is 100 by rho square. So if you differentiate rho square, rho to the power minus 1, what you get? Minus 1 rho to the power minus 2. That means minus 1 by rho square. So this becomes minus 1 by minus 100 by rho square. I repeat, rho by rho square means 1 by rho. 1 by rho means rho to the power minus 1. Apply the formula nx to the power n minus 1. N is minus 1. So if you differentiate 1 by rho, you get minus 1 by rho square. These two derivatives are 0. This is 0 because if you differentiate a function of rho with respect to z, the result is 0. So you get 100 divided by rho cube, so many coulombs per meter cube per second. This is the expression. 100 divided by rho cube, coulombs per meter cube per second. The unit for rho v is coulombs per meter cube. It is differentiated, therefore coulombs per meter cube per second. This is the end of the solution. Thank you. I am happy to say that we have finished 2 modules. Now I am entering 3rd module. The first topic is Laplace and Poisson's equations. Poisson's and Laplace equations. Poisson's and Laplace's equations. Very, very important topic. Very easy. Easy means practice is required. Right? The Gauss law in point form is the Gauss law in point form is divergence of D is equal to rho v. I call this as equation 1. We know that vector D is equal to epsilon into vector E. Equation 2. We shall substitute equation 2 in equation 1. Substituting equation 2 in equation 1, we get del dot epsilon into vector E is equal to rho v. We'll divide both sides by epsilon. So you get what this implies. Del dot vector E is equal to rho v divided by epsilon. Equation 3. Also vector E is equal to minus grad v. Equation 4. Making use of equation 4 in equation 3 gives making use of equation 4 in equation 3 gives what? Del dot, what is vector E minus grad V is equal to rho V by epsilon. Transfer the minus sign onto right side. This implies del dot del V is equal to minus rho V by epsilon. See, note, vector A dot vector A is equal to A square. Grad also is a vector, therefore, hence, del dot del is equal to del square. Del is a vector, del square is a scalar. Please note that. Thus, correct, thus, this equation becomes what? Del square V is equal to minus rho V by epsilon. This is equation 5. What is del square V in Cartesian coordinate system? We shall find. Equation 5 is called Poisson's equation. Equation 5 is defined as or is known as Poisson's equation. Poisson's equation, and is used for finding potential distribution. If you want to find in a diode in the depletion region how potential varies, if you want to find that expression, we have to make use of this equation. When I do problems, I will take some practical examples and tell you. Equation 5 is known as Poisson's equation. If rho V equal to 0, equation 5 reduces to del square V equal to 0. Equation 6 is known as Laplace's equation. Laplace's equation is a special case of Poisson's equation. That means Laplace's equation is applied for a charge-free region. Charge-free region means rho V equal to 0. Poisson, that means Laplace's equation is used for finding potential distribution in a charge-free region. For example, you take a parallel plate capacitor. Charges reside only on the surface of the plates. In the region between the two plates, rho V is 0 because no charges. Therefore, if you want to find how potential varies between the two plates of a parallel plate capacitor, you have to use equation 6, known as Laplace's equation. If rho V not equal to 0, if you want to find the variation of potential with respect to distance, you have to use equation 5. Now, next is expression for del square in different coordinate systems. Note, let us evaluate del dot del V in a Cartesian coordinate system. Del dot del V is equal to, what is del? It is nothing but Ax cap into dou by dou x plus Ay cap dou by dou y plus Az cap dou by dou z dot. What is grad V? Nothing but Ax cap into dou V by dou x plus Ay cap into dou V by dou y plus Az cap into dou by dou z, dou V by dou z. So, if you take dot product of these two vectors, del is a vector, grad V is a vector. If you take dot product, Ax cap dot X cap is 1. So, you get dou by dou x operating on dou V by dou x. This is what you get when you take dot product of these two quantities. When you take dot product of these two quantities, you get what? Dou by dou y operating on dou V by dou y. When you take dot product of these two quantities, you get dou by dou z operating on dou v by dou z. So this becomes dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. This is the expression for del dot del v. Del dot del v is equal to what? Del square v. Equal to del square v. In which system? Cartesian system. Cartesian system. In a cylindrical coordinate system, coordinate system, what is the expression for del square v? Please note that del square is called Laplacian operator. Del square, people call it as, del square is known as Laplacian operator. Laplacian operator. And del square is a scalar. Look at del square v expression. There are no unit vectors ax cap, ay cap, az cap. Therefore, del square is a scalar. Del is a vector. I don't put an arrow explicitly. I don't put an arrow on the top of vector del because it is understood it's a vector. In the textbook we write by a dark letter or by a bold-faced letter. In a cylindrical coordinate system, what are the coordinates? The coordinates are rho, phi and z. So I'll write the expression del square v is equal to 1 by rho, dou by dou rho operating on rho into dou v by dou rho plus 1 by rho square dou by dou phi operating on 1 by rho square dou by dou phi operating on dou v by dou phi. That means dou square v by dou phi square plus dou square v by dou z square. This is the expression for del square v in a cylindrical coordinate system. This gives the variation in rho direction. This gives the variation in phi direction. This gives the variation in z direction. Similarly, in a spherical coordinate system, we have del square v is equal to 1 by r square dou by dou r operating on r square into dou v by dou r plus 1 over r square sin theta dou by dou theta operating on sin theta into dou v by dou theta plus 1 by r square sin square theta operating on 1 over r square sin square theta multiplied by dou square v by dou phi square. I repeat, this is the variation in r direction. This is the variation in theta direction. This is the variation in phi direction. The coordinates in a spherical coordinate system are r, theta, phi. Please remember the coefficients 1 by r square, 1 over r square sin theta, 1 over r square sin square theta. In the cylindrical coordinates, what are the coefficients? 1 by rho square and 1 and 1. These coefficients you please remember. In the examination, problems will be asked on Laplace and Poisson's equations. So you have to remember the expressions for del square v in a Cartesian coordinate system, in a spherical coordinate system, in a cylindrical coordinate system and in a spherical coordinate system. This derivation will be asked in the exam for 6 marks. This much you have to write. Thank you. We shall do now few problems based on Poisson's and Laplace's equations. The first problem in the series is, using Laplace's equation, obtain the potential distribution between two spherical conductors separated by a single dielectric. The inner sphere is of radius equal to A and outer sphere is of radius equal to B. A potential of V0 is applied between the two spheres, with the outer sphere being grounded. Also find the expression for vector E. The problem statement I'll translate it into a figure. We have got two concentric spheres. Inner sphere is of radius equal to A. Outer sphere is of radius equal to B. Outer sphere is grounded. A potential of V0 volts is maintained between the two spheres. The inner sphere is positively charged to plus Q. Outer sphere is negatively charged to minus Q. At a point between the two spheres, no charges reside, therefore rho V equal to 0. Therefore, if you want to find the expression how the potential varies from V0 to 0, see, when R equal to A, V is V, potential is V0. When R equal to B, potential is what? 0. From R equal to A to R equal to B, how potential varies is what we have to find. Correct? What are the coordinates of point P? Coordinates of point P are R, theta, phi. The coordinates of point P, this is point P, it has got coordinates R, theta, phi. At point P, rho V is 0. So the Laplacian equation in a spherical coordinate system, we have to remember. Very, very critical point. If you don't remember this equation, this problem cannot be attempted. These are all very standard problems, asked several times in the examination. Therefore, these problems practice n number of times. The Laplace equation in a spherical coordinate system. In a spherical coordinate system is, please watch, del square V is equal to 1 by R square, dou by dou R, operating on R square into dou V by dou R. This gives variation in R direction, plus 1 by R square sin theta, dou by dou theta operating on sin theta into dou V by dou theta, plus 1 by R square sin square theta into dou square V by dou phi square equal to 0. This gives variation in R direction, this gives variation in theta direction, this gives variation in phi direction. Since V, potential V, is a function of R only, the above equation reduces to. What I want to say is, Laplace's equation is a three-dimensional equation because it has got variation in R direction, variation in theta direction and variation in phi direction. Somehow, this three-dimensional equation has to be reduced into a one-dimensional equation. For that purpose, what I have written, since V is a function of R only, that means when R equal to A, what is the value of V? It is V0. When R equal to B, what is the value of V? Potential V? 0. That means V varies only along the radius of the system. Since V is a function of R only, the above equation reduces to 1 by R square dou by dou R operating on R square into dou V by dou R plus 0 equal to 0. These two variations are 0 because V is a pure function of R only. Now, since 1 by R square cannot be 0, it implies dou by dou R operating on R square into dou V by dou R equal to 0. Integrating with respect to R gives R square into dou V by dou R is equal to K1, where K1 is the constant of integration. This implies dou V by dou R is equal to K1 divided by R square. Again integrating with respect to R, gives Again integrating with respect to r gives v is equal to minus k1 by r plus k2, equation 1. 1 by r square, if you integrate, you get minus 1 by r, where k1 and k2 are the constants of integration. K1 and K2 are the constants of integration and are to be evaluated using suitable boundary conditions. Boundary condition 1. Boundary condition 1. When r is equal to b, v is equal to 0. When r is equal to b, v is 0 because outer sphere is grounded. Accordingly, equation 1 becomes 0 is equal to minus k1 by b plus k2. This implies k2 is equal to k1 by b, equation 2. Boundary condition 2. When r is equal to a, v is equal to v naught, because inner sphere is at a potential of v naught. Hence, equation 1 gives, when you put v equal to v naught, the value of r should be a. Gives what? V naught is equal to minus k1 by a plus k2. This is equation number 3. Using equation 2 in equation 3 gives v naught is equal to minus k1 by a plus what is k2? K2 is what? K1 by b. K2 is what? K1 by b. This implies v naught is equal to K1, if you take common, you get 1 by b minus 1 by a. This implies v naught is equal to K1 into a minus b divided by ab. This implies K1 is equal to v naught into ab divided by a minus b, or minus v naught into ab divided by b minus a. Here I have taken minus sign common. This is the expression for K1. And K2, what is K2? K2 equals K1 by b. What is K1? K1 is what? Minus v naught into ab divided by b minus a into 1 by b. So this gives minus v naught into a divided by b minus a. So by making use of the boundary conditions, we have found the values of K1 and K2. So the methodology is like this. First you have to write Laplace's equation in a spherical coordinate system. It will be a three-dimensional equation. Then by stating that r is a pure function of, v is a pure function of r, the three-dimensional equation must be reduced to one-dimensional equation. Then we have to integrate with respect to r twice. That gives us two integration constants in the form of K1 and K2, and these constants of integration evaluated by making use of the boundary conditions. When r is equal to b, v is 0. When r equal to a, v equals v naught. The constants upon evaluation are found to be K1 equals this much, K2 equals this much. Now the values of K1 and K2 I substitute in equation 1. substituting the values of K1 and K2 in equation 1 gives V is equal to minus, if you substitute, minus of minus becomes plus. So plus V naught into AB divided by B minus A plus K2. K2 is what? Minus V naught into A divided by B minus A into R. So if you put here R equal to B, these two terms will cancel out and you get 0. When you put R equal to A, you will get V is equal to V naught. So what is important over here is, you can check, you put R equal to A. If you put R equal to A, then what happens? This becomes V naught into AB by B minus A. This becomes minus V naught by B minus A. Simplify, you will get the answer as V naught. So this is V naught into AB by B minus A into R minus V naught into A by B minus A. This is the expression for potential variation when R varies from A to B. Now next to find vector E. We know that vector E is equal to minus grad V. In a spherical coordinate system, the expression for gradient has to be recalled. So this is minus dou V by dou R into AR cap plus 1 by R dou V by dou theta into A theta cap plus 1 by R sin theta dou V by dou phi into A phi cap. This is the expression for gradient. In a spherical coordinate system. V is a function of R only. Therefore, dou V by dou theta will be 0 and dou V by dou phi will be 0. This implies vector E is equal to minus dou V by dou R into AR cap. So if you differentiate this with 1 by R, if you differentiate, you get minus 1 by R square. So you get minus V naught into AB divided by B minus A into R square into AR cap. So many volts per meter. This is the expression for, this becomes plus. This is the expression for electric field intensity. So the dou V by dou theta and dou V by dou phi are 0 because V is a pure function of R. 1 by R, if you differentiate, you get minus 1 by R square. That will cancel this minus sign so that you get plus. This is the end of the problem. Thank you.